record on this. Okay, so as I was saying before, go ahead and try to figure out a way to get a schedule such that we can, you can study best and learn best from this kind of opportunity where we have it off, offline reading, offline videos, and then online focusing on the slides that we have and what we're going to be drawing on. Okay, so let's see if I can move to the next slide here. That doesn't like that at all. So move the slide there. Okay. Do we see something that says Texas State Chemistry 2330, Summer 1?
Yes.
Okay, we see that now. Okay, so last time we talked about Chapter 1, Goal 1, which was electrons and the types of bonds they form. Okay, so what we're going to do is continue on that with Lewis dot structures and functional groups. The reason I do this as a group here is because when we start doing Lewis dot structures, it's basically looking at where the bonds forming between different atoms. And by forming those bonds with different atoms, we get different functional groups. So that's why I've lumped these two together. And so that we're going to look at the different sources we have on that. This is going to be a little different because I can't actually do the annotations. So I'm going to try to draw with the mouse. So hopefully that'll at least get us till the point where we can stop at the halfway point, and I'll try to use the other internet connection. Okay, so Lewis did a lot of stuff for us. He helped us track where the electrons are, and the electrons that are most important for us are what we call the valence shell electrons, or the outer electrons, okay? Once a shell has been covered by other electrons, that inner shell is no longer necessary to do that. And so what we'll end up doing is just having the outer electrons are the ones that are going to do all the bonding and all the shapes because of the lone pairs and such. So all we care about is that outermost shell of electrons. And then we have to figure out how many electrons we have to deal with, okay? So, and I said before, we can do that by memorizing these things, or we can, look at our nice table here where, hydrogen, anything in that 1A group will have 1 electron in that Lewis dot structure. Anything in the 5A is going to have 5 electrons to deal with in that Lewis dot structure. And again, we can move to the periodic table of elements that'll help us decide these right here. And when we think about it, this first column here, if actually, let me see. All right, can you see my cursor moving on the screen now? Is there a cursor moving up and down this 1A column?
We actually see your screen, the one that you look at.
The double screen here?
Yeah, the presentation screen.
Okay.
I went from 1 to the double.
Okay. Let me unpresent then and see if I can in slideshow. But I want to still share this screen. All right. Okay, do you see the 1 slide now?
Yes.
Okay, so it's just the 1 slide with the periodic table of elements, and you can see my cursor moving on it, right?
Yes.
Yes.
Okay, good. All righty then. I'll start there then. I'm going to move the chat so I can read it over here. Okay, so again, we don't have to memorize the electrons. We just have to see where it is on the periodic table to help us do that. By the way, I'm trying to figure out a way to have a periodic table available to you on your Top Hat homework and exams. So you can always have this particular table of contents, table of elements to play with, so you'll be very familiar with it and see where to get all these things. Okay, so this A1 column, these all have 1 electron in their outer shell. This A2 column has 2 electrons in their outer shell, which means helium should really be over here. So we have 4 for carbon, 5 for nitrogen, and oxygen. So we don't have to memorize anything. We just need to know which element it is and where it is on the table, and we can use those. So our rules for Lewis dot structure are pretty simple. We need to take the number of valence electrons for the entire molecule. And the easiest way to do that is to take each individual atom and know how many electrons there are around each of them, and then you need to have that many electrons total in your system, okay? So the next thing we have to do is determine connectivity, or the arrangement of the atoms. This is sometimes hard when you're first starting out saying, oh, I don't know which one to do. I'm going to show you some tricks for how to start that. And then as you practice this and recognize certain compounds, you'll see that certain things usually happen, like you try to put 3 or 4 bonds to carbon, and then you start building out from there. Okay, but so determine the connectivity is usually the hardest part to start with, but once you do it a few times, you're going to get it. You're going to connect the atoms with a single line between the atoms. Okay, that's showing that those atoms are fixed in space and attached to each other. And then we're going to arrange all the electrons around all the other atoms. Okay, now what we have to remember is the electron, that line drawing between bonds. If it's a single line, that's 2 electrons, okay? Single line is 2 electrons. A lone pair, which is the 2 dots, are individual electrons, and they typically go in pairs. So those are non-bonding, typically in pairs. That is also 2 electrons. If you have just one line, that's 2 electrons. If you have 2 lines, that's a double bond, so that's 4 electrons. And if you have 3 lines, that's a triple bond, that's 6 electrons. We just need to keep track of that. Each of those lines counts as 2 electrons, and lone pairs count as 2 electrons as well. Occasionally we'll come up with an unpaired electron, and those are called radicals, but we don't have to worry about those until chapter 16. So another thing to think about when we have these Lewis dot structures is that you typically want 4 bonds to carbon and no lone pairs. Okay, so when you're thinking about your structure, a lot of times it works to put the carbon in the middle and draw 4 things out from it, and then we'll see if the connectivity works from there. Nitrogen typically has 3 bonds plus a lone pair, so you might want to draw a nitrogen with 3 lines and put your lone pair on. Oxygen always has 2 bonds and 2 lone pairs. The halogens will have 3 lone pairs and a single bond, okay? So that makes it easy to play with. And hydrogen will have that single bond and no lone pairs. Okay, so using those rules, the rules from this page here and these guides, we can actually start drawing Lewis dot structures for the system. Okay, now let's see if I can annotate with the draw function here. Okay, so let's start with something simple like, let's see if I can do this on here, H2O, okay. So if we have 2 of the same atoms and 1 different atom, we want to start with putting that 1 different atom in the middle. So we're going to start with our oxygen here, and we know our oxygen needs to have 2 bonds, and we have 2 other atoms, so we're going to add those 2 other atoms here, okay. So let's see how many electrons we have. We have hydrogens here. Each of those has 1 electron. So that's 2 electrons for the hydrogens. Oxygen has 6 electrons, right? So we have 2 for the hydrogens plus 6 for the oxygen gives us a total of 8 electrons to play with, okay? Just by drawing here, we have 1, 2 electrons, 3, 4 electrons. We have 4 electrons left to put in our Lewis dot structure. So oxygen always has 2 lone pairs, so let's put those there, right here. So let's see how many electrons we have now. 1, 2, 3, 4, 5, 6, 7, 8, because remember, each of those bonds is 2 electrons. We have a total of 8 electrons in our structure. We needed to use 8 electrons. Oxygen bonds twice and has 2 lone pairs. Oxygen bonds twice and has 2 lone pairs. So that's great. That means we've successfully drawn that Lewis dot structure using those 6 rules plus the guides of how many bonds things have, okay? So let's do one more that's a little more complex and kind of makes it a little bit harder to figure out the first time. And
So
let's
I have
go,
a question.
yes.
So for the H2O, why, how do you know that oxygen has 2 lone pairs and why isn't it just 2 double bonds instead?
Okay, good question. Okay, so so how many electrons does hydrogen need to have in its outer shell?
2.
2. So if we have this bond between the hydrogen and the oxygen, we have one electron here and one electron here. Therefore, hydrogen is sharing 2 electrons. So it only ever has a single bond and no unpaired electrons, right? From our rule on the previous slide. So the hydrogen is satisfied. This hydrogen over here also has 2 electrons that it shares here. So that hydrogen is filling its rule of 1 bond and no lone pairs. And our oxygen has 2 bonds and 2 lone pairs. So it follows its rule.
Okay.
Does that answer your question?
Yes, thank you.
Okay. So let me see. Okay. All right. Let me stop annotating right here. And okay. All right, so I have to stop annotating and go to here. Okay, so, oh, wow. Yeah, here we go. Annotate, clear all drawings. All right, so again, we want to look at these rules, these guidelines right here, in addition to these rules. Total number of electrons, connectivity, single lines equal 2 electrons, start filling up. We want to fill them up in general in this pattern. We need a total of 4 bonds. That could be single bonds or double bonds or triple bonds. We have to figure that out with the number of electrons and the other atoms we have. So let's do something that kind of does a little bit something with that. And I'm going to go back to this annotate function here, draw. And let's do something a little bit different. Let's do hydrogen, and we're going to have 2 of those. We're going to have an oxygen, and we're going to have a carbon, okay? So obviously, that's not how the connectivity is going to work, but we're going to start with our rules and see if we can figure it out here. So the hydrogen each has 1 electron, so that's 2 electrons. The oxygen has 6 electrons, so there's 6 electrons, and the carbon has 4 electrons here. So the total of those is going to give us 12 electrons to play with, okay? Now, we know oxygen needs to bond twice, and we know that carbon needs to bond 4 times. So let's put the carbon in the middle and put oxygen bonded to it, and then a hydrogen bonded to it, and a hydrogen bonded to it, okay? So oxygen still needs 1 more bond, and carbon needs 1 more bond, okay? Now, we have 1 bond here, and that's 2 electrons. We have 1 bond here, and that's 2 electrons, and 1 bond here, and that's 2 electrons. So far, we've used 6 electrons right here, but we have 6 more left, okay? And we know we don't want them on the hydrogens because that can't have a lone pair. And we don't want to just put them on the carbon because the carbon doesn't have lone pair either, okay? But the oxygen typically has 2 lone pairs. So let's take 2 of those electrons and put them here, and 2 of them put them here, okay? So that's a total of 4 of those 6 left electrons. Now we only have 2 electrons left, okay? So our oxygen has 2 lone pairs on it. Our hydrogens are satisfied. Our carbon still needs another bond, and our oxygen still needs another bond. But we've taken care of our lone pairs. We have 2 electrons left. So we can't put another bond between the hydrogen and the carbon because it only bonds once, but we can put a bond here. Okay, if we put the bond there, now carbon has 4 bonds, oxygen has 2 bonds, and oxygen has 2 lone pairs. So we satisfied all of our rules by trying to put the most number of bonds to the thing that bonds the most. So if we didn't have carbon, we only had nitrogen, we'd want to put nitrogen in the middle first because it would bond the most number of times. So by following that little strategy, I think we can get to really complex things and get them done. All right, I'm going to clear this and stop annotating and move to something a little more complex on the next slide here. Let's do something, and there's ones on the bottom here, and so if you go back and look at the slides and do them additionally, you'll get some additional practice on that. Let's do something a little more complex. Let's do H NC. Okay? Boy, that's going to be hard to do because we don't really have that many atoms. And we have a whole bunch of bonds to deal with here. So let's figure this out here. Okay, so hydrogen has 1 electron, nitrogen has 5 electrons, and carbon has 4 electrons. So we have a total of 10 electrons to play with. Okay, and nitrogen bonds 3 times, carbon bonds 4 times. So I'm going to put carbon in the middle because carbon has to bond more times. So we have nitrogen here, and we have hydrogen here. Okay. Carbon never has lone pairs, so I can't put any electrons there. Nitrogen usually bonds 3 times and has a lone pair. So I'm going to put a lone pair here just to see where we're going with this. Okay. So that's the basic connectivity, and we've added all the lone pairs we need. So let's count how many electrons we have. 1, 2, 3, 4, 5, 6. So we've used up 6. That means we have 4 electrons left, okay? Not only do we have 4 electrons left, we also have 2 bonds left for carbon and 2 bonds left for nitrogen. Each bond is 2 electrons. So let's add 2 more electrons here. So carbon now has 3 bonds, not quite happy. So let's add a 4th bond here. So carbon has 4 bonds and it has a total of 8 electrons around it. Nitrogen has 3 bonds plus a lone pair, and hydrogen has 1 bond and no lone pair. So we followed all the rules. Now let's count up our electrons and see if they're right. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. All right, so we have 10 electrons. We have a valid Lewis dot structure. Okay? All right, what do you think about that process of trying to put the most connected thing in the middle and then add your connectivity and then add your lone pairs and then try to get the rest of the electrons to fill in the rest of the bonds? Okay? Okay, so it's kind of nice and stepwise, and hopefully it can, you can practice that more. And so there's some structures down here on the bottom of these slides that you'll see. And if you go ahead and practice this using those steps, I think you'll see it easy that you can get any kind of crazy combination of atoms together in this kind of 3D structure. Okay, all right, I'm gonna clear this. Since it'll be on the video, so we can see that on the video. And let's move on to our next slide here. Okay. The next thing I want to talk about is once we've done our Lewis dot structure and we have the right number of electrons and the right number of bonds, we actually want to do something called the calculation of formal charge. What this will do for us is it'll say that, okay, within a molecule, the molecule itself could be neutral, but the individual atoms in the molecule can have charge, okay? And so what'll happen is you might have something that has a formal charge of +1 and a formal charge of -1 in the same molecule. So the molecule itself will be neutral, but you'll have reactivity based on where that formal charge is. In addition to that, you can actually have a charged species. So like the acetate ion or an azide ion, which will have charge, but you might have different charges on different atoms in there. So the formal charge is basically looking at how many electrons are actually around each individual atom. And so we calculate formal charge for every atom in a species, okay, in a molecule. So formal charge, or FC here, is equal to the number of valence electrons in a neutral unbound atom, which is basically the valence electron it brings to your Lewis dot structure, okay? And you're gonna subtract all unshared electrons, and those are typically the electron pairs, or occasionally you'll have a radical there. So those are things that are not shared with other atoms, okay? So they're like lone pairs or a single electron residing on that atom. And then you add to that half of the bonded electrons, okay? Why? Okay, remember, when you're bonding, you're sharing those electrons, which means you only get a full electron 100% of the time and a partial electron part of the time. So we're going to use half of the bonded electrons to do our calculation. Okay, so let's go ahead and calculate this middle one here, the acetate ion. I'm going to go ahead and annotate again here. So the first thing we're going to want to do is we're going to want to draw a valid Lewis dot structure before we can calculate formal charge. And then we need to calculate the formal charge on each atom, okay? So I'm gonna do that for the acetate ion, which is CH3COO minus, okay? So that minus, we have to think that we're gonna add an electron there. So we're going to draw the acetate ion as C, O, O, C, and then there's an H here, there's an H here, there's an H here, and let's see, oxygen likes to have 2 lone pairs, so we're going to draw that there, and then but 2 bonds, and this likes to have 2 bonds, but because we have a negative charge, we're going to end up putting that last electron that would normally be shared with something with this here. Now, why do I know there's a negative charge here? Okay, because we have an electron here. Oxygen brought 6 electrons. It has 6 valence electrons, right? So one of those valence electrons is here, then the 4 for the lone pair. This would be in the neutral species of oxygen, okay? Because we have a negative charge, that means we have at least 1 more electron than protons. So that's where this last electron comes from, the fact that we have that negative charge here. Okay, so now that we've drawn this Lewis dot structure with our negative charge, that negative charge takes up that second bond, basically, that it would try to form to get its full outer shell. Okay, all right, so now let's calculate formal charge for this first carbon here. I'm gonna change the color. Can I change color here? All right, so I'm gonna do it for this carbon first, okay? So I have a carbon here, and it has its formal charge is equal to, the number of valence electrons it has minus non-bonded electrons. Sorry, that's a B. Plus 1/2 of the bonded electrons. Okay, so this carbon has 4 bonds total. And so that's a total of 8 electrons. And so 1/2 of 8 is 4. We have 0 non-bonded electrons. There's no electron pairs here. And it brought 4 electrons with it because it's in group A4. So we have the total equation is going to be 4 minus 0 plus 4, which gives us a formal charge of 0 on that carbon. So there's a formal charge of 0 on this carbon. Okay. So let's change colors again to this color, and we're going to do formal charge on this carbon here. Okay. So we had 4 valence electrons it brought to the party. We have 1, 2, 3, 4 bonds to it. So we have 0 non-bonding electrons. And we're going to plus 1/2 of 8 electrons. So that's going to be 4, which is going to mean the charge on that carbon is going to be, again, equal to 0. So this is also a formal charge of 0. Okay. Let's now do that oxygen. Okay, and I'm going to do it in red now. So we're going to do this one here. Okay, so formal charge is going to be equal to the number of valence electrons it brought with it, which is 6 because it's in group A6, right here. And then we have minus the, let's see, the number of electrons that are non-bonding, 1, 2, 3, 4, 5, 6 non-bonding electrons, plus 1/2 of the bonding electrons. We have 1 bond to carbon here, so that's a total of 2 electrons. So 1/2 of 2 is 7. So we have 7 minus 6 is equal to our formal charge, okay? So 6 minus 7 is equal to -1. That means the formal charge on this oxygen is -1, okay? So we can do this with all sorts of compounds here. It's always the same equations. Just make sure you're thinking every single line is 2 electrons, and those are bonded electrons. Lone pairs are individual electrons and count all to themselves. And the number of valence electrons is the number of valence electrons in the neutral atom. If you follow all 3 of those, you'll get to a correct value for the formal charge, okay? So I'm going to clear this and move to my next slide right here. Okay, the next thing I want to talk about is resonance, okay? And resonance is when we take our charged species, most often it's a charged species, occasionally it's a neutral species, and we look at the Lewis dot structure and say, hey, why did we draw that acetate ion with the charge on this oxygen and not that oxygen, okay? So, well, the reason is, well, maybe it's just, that's one of the possible Lewis structures that actually exist. We could redraw it such that it was on the other oxygen. When we redraw it to such it's on the other oxygen, that means that we have 2 valid structures. If we have more than 1 valid structure, and it can be either one and go back and forth between the 2, that means we have resonance, okay? Now, there's a couple rules for resonance, and I'm going to talk about those in a minute. And so when we look at this structure, when we drew that acetate ion, we could have those electrons from that negative charge come in and move to give us the electrons charged at some other location. And we do that using a double-headed arrow in a curved line, okay? Saying the electrons are curving over to here, and there's 2 barbs on there because we have 2 electrons. We do actually have a single barbed one, which means a single electron's moving. That's why we always use the double one, okay? So when we can draw 2 or more of valid Lewis dot structures, we have resonance. And the real structure is some hybrid of the combination of 2 or more of those resonance structures. Okay, so let's look at that again. Okay, so in this example, we have a carbonate ion, okay? In the carbonate ion, we have 3 oxygens, and when we draw our Lewis dot structure, there's a charge on each of 2 of the oxygens and no charge on that last oxygen. Okay, but is that last oxygen unique or different from the other 2 oxygens? No, which means that we can have this structure here is only 1 valid Lewis dot structure, okay? If we take these electrons and move them into here, right here, we cannot keep this other bond here because we can only have 4 bonds to carbon. So these electrons that form this bond have to move up to this oxygen. When it does that, this oxygen now has a formal charge of 0, and this oxygen that had a formal charge of 0 now has a formal charge of -1. But they're both valid Lewis dot structures. So that means it can go back and forth, and all we've done is moved electrons. We haven't broken any bonds. We haven't broken the connectivity between those atoms. All we've done is moved electrons. And the net formal charge is the same. Okay, we've just changed the formal charge from moving from this oxygen here to this oxygen here. Now, we have a total of 3 oxygens. Why can't we have this last oxygen over here have the formal charge of 0? Well, we can, and that's a valid Lewis dot structure. Now our formal charge at this one is now 0, and our formal charge at these two is now -1, okay? And again, all we moved was electrons. We did not change the connectivity. We did not change the net charge of the molecule. All we did was move electrons. And that's when we have more than one electronic structure in a Lewis structure can be a valid Lewis dot structure. We haven't changed connectivity and we haven't changed formal charge. That is resonance. Okay, questions on that real quick? Okay, so Lewis dot structures tell us where all the electrons are. Formal charge tells us if there's a charge in a species. If we can have more than one, we now have resonance, okay? So they've kind of added together, each individual rule there is adding together to give us a new thing to talk about, okay? So once we have resonance, we always want to use a curved arrow with 2 barbs. We can only move electrons, okay? And you have to move them to either between 2 atoms or move them onto an atom. You cannot jump over a bond and move the electrons from one atom to another atom. You can only move from non-bonded to bonded and bonded to non-bonded. And in that configuration, you cannot jump around atoms. You'll see them move just one place and then the electrons move one place. Now, this kind of idea of pushing electrons, we do a lot. It helps us with resonance. It helps us showing mechanisms. It helps us showing how things react and why things react, okay? So that's why we want to really take charge of understanding that this curved arrow with 2 barbs is our electrons moving to give us difference in reaction, okay? So additional, just to drive this home, is that to be a contributing structure, they must all have the same number of valence electrons. And that means we follow the rules with 2 electrons to hydrogen, 8 electrons to carbon, nitrogen, oxygen. And if we go to higher elements like phosphorus and sulfur, occasionally you'll have more, like up to 12 electrons in their valence shell. And so we'll see some weird bondings with sulfur and phosphorus, but most of the time with carbon, nitrogen, oxygen, we're going to see the 8 electrons, and we're looking for that. Now, we have not changed the total charge of the system. We still have the same number of valence electrons. We've only changed which atoms they're on. So you have to have the same number of valence electrons, but you're just pushing them around to reside on different elements at different times, okay? So that being said, I've drawn this once before. I'm going to draw it quickly. And so let's draw it in this color here. So I'm going to draw the first one here, just the acetate ion. And I'm going to put the dots here because there's a lone pair on that oxygen there. I'm just going to draw this as a CH3, okay? Because these electrons do not move around in our resonance structure. Only the ones on between the oxygens move. So I'm going to draw these electrons here. And again, this has a negative charge because of that extra electron, okay? So what's going to happen in these systems, I'm going to change the color of my arrow. These electrons are going to move in to form the bond between here, okay? So we have a formal charge of -1 on this oxygen at this time. We have a formal charge of 0 on this oxygen at this time, okay? So this is going to be a double-ended arrow because either one of these structures is fully appropriate, okay? And then what will happen is when I move these here, if I didn't move the electrons from this bond here, we would have 5 bonds to carbon, and it doesn't want 5 bonds. So these electrons are going to be the electrons that become the lone pair on this oxygen. Okay, that's going to give us our new structure, which is oxygen with 3 lone pairs up here and our negative charge. We now have 2 bonds down to here, and we still have our CH3 over here that hasn't changed at all. Okay. Okay, we have the same number of connections, we have the same number of electrons, we have the same formal charge on the whole molecule. It's just now the formal charge on here is 0 and the formal charge on here is -1. So that's how we represent the resonant structure between them. Okay, so if this is going back and forth, and we don't want to draw both of them, let's change the way we draw this. Instead of saying it's this structure or that structure, let's draw a hybrid structure that is in between them, okay? So how would we do that, okay? So instead of having this negative charge here and this negative charge here going back and forth, let's redraw it such that we have a partial bond here and a partial negative charge here and a partial negative charge here. We're going to see this a lot sometimes, is that we'll have a charge spread out over 3 atoms here. So half the time the negative charge is on this atom, half the time the negative charge is on this atom. And this is what we call a resonance hybrid structure, where you don't have to draw both of them, you're just drawing the one showing it's halfway between them. So if we tried to draw the formal charge here, the formal charge would be -1/2, because only half the time is it negative, and this would be -1/2, because only half the time it's negative, okay? So if you draw that for carbonate ion and showing that kind of resonant structure around, you'll get the hang of that and do that again. Okay, so I'm gonna clear this, and we're gonna move on to the next slide. Right here. Okay, I'm going to do this last little thing with the different functional groups. It's going to be short, and then we're going to go ahead and take our break and stop the meeting and try again. And I'm going to try to hook up the internet to the other side of it. Okay, so in functional groups, what we can have is we have atoms, and we know how much they want to bond, and we know how they want their electrons to be. And so we can have them bond in a variety of different ways. If we take the same atoms and bond them differently, they react differently. If they react differently, that means they have different chemical characteristics. They have different boiling points and melting points and everything like that. So when we take the same atoms and rearrange them in a different way, we call those functional groups, okay? And so the first functional group we want to talk about is the alcohol group. It's a nice friend of mine, and I use it a lot. But so the idea here is that an alcohol always contains a carbon bonded to an oxygen bonded to a hydrogen, okay? That's the alcohol group. You must have that oxygen bonded to a carbon and to a hydrogen, okay? If that oxygen is only bonded to 2 hydrogens, that's water. If that oxygen is bonded to 2 carbons, that's a different functional group. So carbon, oxygen, hydrogen is the alcohol functionality. We have a whole chapter on this and a whole bunch about its reactivity, okay? The next one I want to talk about is amines. Amines are kind of cool because you have nitrogen and it wants to bond 3 times, right? So if it's bonded to 1 carbon, we have 1 type of amine because it has 2 hydrogens on it, and those hydrogens do some kinds of chemistry. We can have 2 carbons bonded to it and still have a hydrogen on it, and that'll have different chemistry. And we can also take away all those hydrogens on that nitrogen and have 3 carbons bonded to it. And what we'll learn about in chapter 10 is that we call those different things by having 1 carbon, it's a primary amine, 2 carbons, it's a secondary amine, and 3 carbons, it's a tertiary amine. And we'll learn about how they change their reactivity and their physical properties just by changing that connection. All right, the next functional group involves the carbonyl group. The carbonyl group is a group that is C double bond O, okay? C double bond O. So we have a sigma bond in between and a pi bond over that, and it has a certain shape. When we look at our hybridization, it has the shape of a trigonal planar thing. So we have several different functional groups that involve the carbonyl group, okay? But they all have that C double bond O, okay? If that C double bond O has a carbon and a hydrogen bonded to that carbon, it is an aldehyde, okay? That has a certain type of reactivity. We have to have a carbon, carbonyl, hydrogen is the aldehyde. Let's take that hydrogen off and add another carbon to it. So now we have a carbon, carbonyl, carbon. That's another functional group. It's called a ketone. And they have typically pleasant smells and are used a lot in biological systems, okay? Now, if we take that carbonyl and instead of having a hydrogen bonded to it, we bond an OH to it, we have our next functional group. So we have a carbon bonded to a carbonyl bonded to an OH. So imagine we're taking an aldehyde, an alcohol, which is that COH, and taking that and transferring it to a carbonyl. We have a completely different functional group called the carboxylic acid, okay? And there's a wide variety of derivatives we have with this, okay? So just that different connectivity of different atoms gives us different functional groups. And we're gonna go through each one of these functional groups throughout the chapter here. So the summary for this goal is that valence electrons do all the bonding. Lewis dot structures show our valence electrons, and we use those 7 rules to get valid structures of connectivity and where the electrons are. Formal charge is used on each and every atom in a molecule, and it will give you the overall charge of the compound. The Lewis dot structure plus a formal charge can give us where the resonance or resonance hybrid might be. And by taking the same atoms and bonding them in different ways so you have different configurations, gives you different functional groups. Okay, so that is chapter 1, goal 2. And what I'm gonna go ahead and do is I'm going to stop recording, and let me stop sharing first, and I'm gonna stop recording